Hello, today we want to prove the general AMGM inequality. So last time we did this inequality for rational PIs. Now we do it for general real numbers. We only condition that the AIs are positive real numbers and these PIs, as said, can be general real numbers. They still have to be positive and they all sum up to 1. So what changed now is only that we only don't constrain this to rational numbers. Okay, let's prove this. Before we prove this, we have to prove a small lemma. So we will use the following inequality. 1 plus x is always smaller or equal to e to the power of x for x bigger or equal to 0. Let's prove this lemma. So if we define a function f of x, which is e to the power of x minus 1, then we differentiate this function. F prime of x is e to the power of x minus 1. And so we know that this is always bigger or equal to 0 if x is bigger or equal to 0. So it only gets 0 if x is 0, because then e to the power of 0 is 1 minus 1 is 0. Okay. Now, what can we infer from this? If the first derivative is bigger or equal to 0, then we know that f is monotonically increasing. Okay, so we know that it's monotonically increasing, and we also have the smallest point, f of 0, is equal to e to the power of 0 minus 1, which is then just 1 minus 1, which is 0. So all the other, for all the other x's that are bigger than 0, the function has to be bigger or equal to 0. So generally we can say that f of x, which is e to the power of x minus 1, is bigger or equal to 0 for all x bigger or equal to 0. So this implies if we bring these two guys here to the right-hand side, then we have e to the power of x bigger or equal to x plus 1, which is what we wanted to show in this lemma. Okay, so why do we condition for our x's to be positives? We only deal with positive a's, so the a's will be inserted into the place of the x. Okay, so instead of using 1 plus x equals e to the power of x, we can also write it in the following way. We can insert into this x x minus 1. So let's do that. Then we have x minus 1 is smaller or equal to e to the power of x minus 1. So it's basically the same thing. We just rewrote the inequality a little bit. And so this is the thing that we are going to use from now on. Oh, oops, sorry, that's actually not true. That is only x smaller or equal e to the power of x minus 1. For x, of course, bigger or equal to 0. Now we want to use the AIs for these x's. So we have AI smaller or equal to e to the power of I minus 1. And if we take this to the power of something positive, so this is positive and this is positive. So if we take this inequality to the positive of a pi, the inequality is preserved and we get ai to the power of pi is smaller or equal to e to the power of pi, ai minus pi. Since we only deal with positive real numbers, we can multiply all of these inequalities and the inequalities are still preserved. So if we have a1 to the power of p1 times a2 to the power of p2, so on and so forth, then we have an to the power of pn smaller or equal to e to the power of p1 a1 minus p1 e to the power of pn an minus pn. Okay, so the right-hand side, since we have the same base, we can write the exponentials together. They will be summed up. So first we have a summation of all these pi's and ai's from 1 to n minus the summation of all of these pi's to n. And this becomes summation of pi times ai from 1 to n minus 1, because remember, these will sum up to 1. Okay. Now we define something new. We define a to be the summation of these pi times ai from 1 to n. And the next step is to use this inequality for different a's, namely when we normalize them. So all of these ai's will be divided by a. Now let's see what happens. So we have a1 divided by a to the power of p1, and so forth, and an to the power divided by a to the power of pn, and this is smaller or equal. We follow this inequality above strictly, so that you see what happens. So it's then summation of pi ai divided by a, because remember, everywhere we see an ai, we insert this normalization factor. So we have ai divided by a, and then we have a minus 1. Okay, so here we have a in the summation, we can pull this 1 over a out, and then we have the summation of pi times ai from 1 to n. Then we have a minus 1. So that's very interesting, because this here is actually a. This is the way we defined our a. So this cancels with this one. And then we have e to the power of 1 minus 1, which is then, of course, e to the power of 0. And then we have a 1. Okay, next step will be to multiply all of these factors, these a's, to the right-hand side. So we have a1 to the power of p1 until an to the power of pn is smaller or equal a to the power of p1, because remember, we cannot just pull this out. We have to consider the exponential. So it will be potentiated with p1. So we have this till pn. And since, again, this is the same base, so we can sum up all of these pi's from 1 to n. And of course, we know from our precondition, this is 1. And so we get a to the power of 1, or just a. And what was a? A was just the summation, p1 times a1, so forth, until pn times an. And that's basically it. That's the general arithmetic geometric inequality.